A machine floating 1 million miles from Earth is rewriting everything we thought we knew about the cosmos. Not gradually, not incrementally, but fundamentally, in ways that have left some of the most experienced astronomers on the planet openly admitting they don't understand what they're seeing. The James Webb Space Telescope has been staring into the infrared darkness for a few years now, and what it has found challenges decades of carefully constructed theory about how the universe formed, how galaxies grew, how black holes got so massive, and what the earliest moments of cosmic history actually looked like. We're going to go through all of it tonight, discovery by discovery, building a genuine picture of what Webb has found and why it matters so much. By the time we're done, you'll understand not just what Webb saw, but why it saw it, why infrared matters, why distance equals time, and why some of these discoveries are genuinely making cosmologists nervous in the best possible way. This is not a list of impressive facts strung together to sound dramatic. This is a coherent story about what humanity's most powerful eye in the sky has revealed about the universe, and why that revelation is so significant. The telescope itself sits at a location called the second Lagrange point, a gravitational sweet spot about 1 million miles from Earth in the direction away from the Sun, where the gravitational pulls of Earth and Sun balance in a way that allows an object to orbit the Sun at the same rate Earth does, staying in a fixed position relative to our planet without needing constant fuel expenditure to maintain its location. This is not where Hubble lives. Hubble orbits Earth directly, swinging around the planet every 95 minutes at a few hundred miles altitude, which means it spends a significant fraction of each orbit passing through Earth's shadow or with Earth blocking part of its view. Webb is much farther out, sitting in a stable gravitational harbour that gives it a clear, unobstructed view of deep space. From the second Lagrange point, Earth, Sun and Moon all stay in roughly the same direction, which makes it possible to shield the telescope from the heat and light of all three simultaneously using a single large sunshield. The telescope's mirror is 6.5 meters across, made of 18 hexagonal segments coated in a thin layer of gold because gold reflects infrared light particularly well. The total light collecting area is about 6 times larger than Hubble's mirror, which means Webb gathers roughly 6 times as many photons per unit time from any given source. More photons means fainter objects become detectable that would otherwise be completely invisible, and it means that objects bright enough to detect can be studied with much higher precision and in much greater spectral detail. Behind the mirror sits a sun shield the size of a tennis court, a 5-layer structure made of a material called kapton, coated with aluminum and silicon that blocks heat and light from the Sun, Earth and Moon simultaneously. The sun shield reduces incoming heat by a factor of roughly 1 million, dropping the temperature of the cold side of the telescope to about negative 233 degrees Celsius, just 40 degrees above absolute zero. This extreme cold is essential because Webb observes primarily in infrared wavelengths, which are essentially heat radiation, and if the telescope itself were warm, it would blind its own instruments with its own thermal emission, the way a hot rock glowing in darkness would blind a camera trying to photograph a faint candle behind it. Why infrared specifically? Because the universe is expanding. This is not a poetic statement. It is a physical reality with direct consequences for how we observe distant objects. When the universe expands, it stretches the space between galaxies, and light traveling through that expanding space gets stretched along with it. Wavelengths increase. The light shifts toward the red end of the spectrum, and eventually beyond red into the infrared. For the most distant galaxies, light that left them as ultraviolet radiation when the universe was young has been stretched so dramatically by 13+ billion years of cosmic expansion that it arrives at Earth as infrared radiation. Hubble couldn't see this. Its cameras were optimized for visible light and near-infrared, which meant there was a wall beyond a certain distance at which galaxies became effectively invisible to it, no matter how long you exposed the detector. Webb was built specifically to see past that wall, to collect the ancient, stretched infrared light from the earliest galaxies and translate it into data we can analyze and understand. Every design choice, from the gold mirror coating to the refrigerating sun shield to the location at the second Lagrange point, was made in service of this core capability. The telescope launched on Christmas Day 2021. The launch itself was the easier part of the process, relatively speaking. After separation from the Ariane 5 rocket, Webb had to deploy itself autonomously over the course of several weeks, unfolding from its compact launch configuration into its operational form. The sun shield had to unfurl, each of its 5 layers tensioning precisely into position, without any of the countless connections snagging or tearing. The secondary mirror, which sits at the end of a tripod-like structure in front of the primary mirror, had to swing out into place and lock. The primary mirror segments had to unfold from their folded launch position and then be aligned with each other to nanometer precision, using tiny actuators behind each segment that could make adjustments smaller than a fraction of the wavelength of light. In total, 1,044 individual things had to work correctly in sequence for the mission to succeed. A single failure in the wrong place could have ended everything. Every step worked. Every panel unfolded, every actuator responded, every instrument activated, every mirror segment aligned. Engineers who had spent 20 years building this machine held their breath for months and then exhaled with relief as the telescope opened its eye and began collecting light from the early universe. Each observation Webb makes is a journey into the past. This is not a figure of speech or a metaphor. Light travels at a finite speed, approximately 300,000 kilometers per second, which is extraordinarily fast by any human standard, but not instantaneous. When you observe a galaxy 1 billion light years away, the light you're receiving left that galaxy 1 billion years ago. You're not seeing the galaxy as it is now. You're seeing it as it was 1 billion years in the past. The further away you look, the further back in time you see. This is a fundamental consequence of the finite speed of light combined with the vast scale of the cosmos. Webb pushes this principle to an extreme that staggers the imagination. The telescope routinely captures photons that began their journey when the universe was less than 5% of its current age. Those photons have been traveling through continuously expanding space for more than 13 billion years. When they finally hit Webb's detectors after all that time and all that distance, they carry information about galaxies that existed when the cosmos was an infant, when the universe was still in the process of assembling its first structures from the hot, dense soup left over from the Big Bang. Studying them is as close as we can come to having a time machine. Before Webb began operating, astronomers had a reasonably confident picture of what those early galaxies should look like. The standard model of cosmology, developed over decades of careful theoretical work and backed by extensive observational evidence from Hubble, ground-based telescopes, and cosmic microwave background satellites, predicted that early galaxies should be small, faint, and structurally simple. The reasoning was straightforward. The universe simply hadn't had time to build anything large or complex. Galaxy formation takes time. Matter has to clump together under gravity, gas has to cool and collapse into stars. Those stars live and die and enrich the surrounding gas with heavy elements through their deaths, and successive generations of stars build up the stellar mass of a galaxy over billions of years. The very earliest galaxies, those that formed in the first few 100 million years after the Big Bang, should show the universe in its infancy, modest and unimpressive by later standards. They should look like the scattered, irregular, small blobs we see at moderate distances in deep Hubble images, but even smaller and fainter and less organized. Webb shattered these expectations in its first week of operation, not in the sense of finding one anomalous object that required an explanation, in the sense of finding a consistent population of galaxies that didn't fit the framework at all. The galaxies it found in the early universe were wrong. Not slightly wrong, not at the margins of what theory predicted. Dramatically wrong. They were too big, too bright, and too structurally mature for their age. Some had already assembled massive stellar populations that should have taken billions of years to build through conventional galaxy formation processes. Some showed organization and structure that models said wouldn't develop until much later epochs. The degree of surprise among astronomers was genuine and immediate, not the managed excitement of press releases, but the genuine bewilderment of scientists confronted with data that contradicts their best models. One researcher described the results as completely unanticipated. Another said it might break cosmology. These were not people given to hyperbole. These were careful scientists looking at real data and finding that it didn't fit the framework they had spent careers developing and refining. Something about our understanding of how the early universe worked was wrong, and Webb was showing us exactly how wrong. The galaxy catalogued as JWST 14-0, which astronomers refer to informally as JDs, became the most striking single example of what Webb was finding. The light from this galaxy has been stretched by a factor of 15 during its journey through expanding space, shifted from ultraviolet wavelengths at emission to infrared wavelengths at detection. It existed just 290 million years after the Big Bang, when the universe was only about 2% of its current age. The cosmos had barely begun. There had been almost no time for matter to assemble into galaxies, for stars to ignite and burn, for any of the processes of galaxy formation that we understand to operate for any meaningful duration. In 290 million years of cosmic time, all of galaxy formation, from the first collapse of gas clouds to the object Webb observed, had to have occurred. And yet JDS exists. It spans more than 1,600 light-years in diameter. It glows with the combined light of enormous numbers of actively forming stars. It has a mass of hundreds of millions of solar masses in stars. It is, by any reasonable measure, a surprisingly mature object for something that formed when the universe was barely getting started. Astronomers stared at the data for months after the initial discovery. The natural assumption when you find something that breaks the rules is that you've made a mistake somewhere. Someone made an error in the spectral analysis. There's contamination from a foreground object. The reduction pipeline introduced an artifact. The redshift measurement is wrong. They checked and rechecked the measurements from multiple angles, looked for instrumental artifacts in the Webb data, considered alternative explanations for the spectral features, ran independent analyses with different software. The measurements held firm every time. This was not a mistake. JWST is real, and it is what it appears to be. And crucially, the brightness of JWST implies something even more significant than the existence of one exceptional galaxy. Webb's sensitivity is high enough that it could have detected a galaxy 10 times fainter than JWST at the same distance. The fact that JWST is so bright means there must be a large population of fainter galaxies from the same era that Webb is also detecting, but that represent the more typical members of the population. And it implies that even earlier galaxies, from before 290 million years after the Big Bang, are waiting to be discovered as Webb continues its observations. The depth of the problem becomes clearer when you consider what powers JWST's brightness. A galaxy can be luminous for two fundamentally different reasons. It can contain an active galactic nucleus, a supermassive black hole consuming surrounding matter and releasing energy equivalent to billions of suns from a tiny central region. Or it can be forming stars at a prodigious rate, with massive young hot stars blazing with ultraviolet radiation that illuminates the surrounding gas. Both mechanisms can produce an extremely bright galaxy, but they leave different spectral fingerprints. Black holes concentrate luminosity into a point source and produce specific emission line signatures in their spectra. Star formation produces broader emission and absorption features characteristic of stellar populations spread across a larger physical area. The spectral analysis of JWST indicates that its brightness comes primarily from star formation, not from a central black hole. This is the more puzzling option, because forming stars is not an instantaneous process. You need gas, you need the gas to cool and collapse over timescales of millions of years. You need the collapse to produce protostars that then take additional time to ignite nuclear fusion. None of this is fast, and JWST simply should not have had enough time for this much star formation to have occurred. But it did. Several possible explanations have been proposed by theorists working to understand what Webb is finding. Some suggest that star formation was simply more efficient in the early universe than it is today. In the present-day universe, only a small fraction of the gas in any given molecular cloud actually ends up in stars. The vast majority is blown away by stellar winds, supernova explosions, and radiation pressure from newly formed massive stars before it can collapse to form additional stars. This is what astronomers call feedback, the self-regulating effect by which stars disrupt the gas supply that forms them. If feedback was weaker in the early universe, perhaps because the first galaxies were more compact and the gas dynamics were different, then a larger fraction of available gas could have been converted into stars in any burst of star formation, making galaxies more luminous per unit of gas consumed and potentially explaining the unexpected brightness. This idea is plausible and has some theoretical support, but the efficiency enhancement required to explain the most extreme cases is larger than most models comfortably accommodate. Others propose that dark matter halos, the vast invisible structures of dark matter within which galaxies form, assembled more rapidly in the early universe than our standard cosmological model predicts. Dark matter is the gravitational scaffold on which visible galaxies are built. Gas falls into the gravitational wells created by dark matter halos and is compressed until it can form stars. If the halos assembled faster than expected, the galaxies within them could have built up their stellar mass more quickly and reached greater luminosities at earlier times. This might require modifications to our understanding of how dark matter behaves on small scales, where observations in nearby galaxies have already suggested some tension with the predictions of the simplest dark matter models. Whether small-scale dark matter modifications could be large enough to explain the early universe galaxy brightness excess without contradicting other observations is currently being actively debated. Others have pointed to the possibility that the initial density fluctuations left over from cosmic inflation, the tiny variations in density that seeded all future structure formation, were not quite as smooth and featureless as the standard model assumes. If certain regions of space started with slightly higher density than average, galaxy formation in those regions could have proceeded faster than in typical regions, producing more massive and more luminous galaxies at earlier times. This would require departures from the scale invariant spectrum of density fluctuations that the simplest inflation models predict, but more complex inflationary models can accommodate such features. The discovery of jades and the broader population of unexpectedly bright early galaxies extended our view into cosmic history by roughly 40% in just 18 months of Webb observations, and every new galaxy found at these extreme distances adds another piece to a puzzle that refuses to fit together neatly. And then Webb found something that made the early galaxy brightness problem look modest by comparison. In the modern universe, there is a relationship between the mass of the stars in a galaxy and the mass of the supermassive black hole at its center that holds across an enormous range of galaxy types and sizes. For every roughly 10,000 solar masses of stars in a galaxy, there is approximately one solar mass in the central black hole. This ratio is not a theoretical prediction. It's an empirical observation confirmed in hundreds of galaxies across cosmic time. The Milky Way follows it. Every massive elliptical galaxy nearby follows it. It's so consistent that astronomers built entire theoretical frameworks around it, concluding that galaxies and their central black holes must grow together in some kind of co-evolutionary relationship, regulated by feedback processes that link the growth of one to the growth of the other in a way that maintains the ratio over billions of years of evolution. Webb found galaxies from the early universe where this relationship is violated by a factor of 1,000. In one striking example, a galaxy observed from when the universe was only 570 million years old showed a central black hole equal to roughly 10% of the total stellar mass of the galaxy. Where modern galaxies have one solar mass of black hole for every 10,000 solar masses of stars, this early galaxy had one solar mass of black hole for every 10 solar masses of stars. The black hole didn't just sit quietly at the center of the galaxy. It dominated the entire system gravitationally, energetically, and in terms of mass budget. The proportions are as alien as if your heart weighed nearly as much as your entire body. The galaxy's identity had been hijacked by its own central black hole. Webb found dozens of these objects in its early observations, and systematic surveys have since confirmed that they appear across a range of early cosmic epochs, suggesting not a handful of bizarre outliers, but a genuine and previously unknown population of objects with shared characteristics. These overmassive black hole systems appear as small red dots in deep field images, a characteristic appearance that has led astronomers to call them little red dots, a deliberately vague descriptor for objects whose nature remains genuinely uncertain. The red color comes from hot gas swirling into the black hole. As matter accelerates toward the event horizon, the intense compression and friction heat it to millions of degrees, causing it to radiate intensely across the electromagnetic spectrum. Dust surrounding the system absorbs the shorter wavelength radiation and re-radiates it at longer wavelengths, further reddening the appearance. The result is a compact, blazing core that can outshine the surrounding stars by enormous factors while appearing distinctly red in Webb's infrared images. The little red dots are so compact that they appear as point sources even to Webb's sharp optics, yet so bright that they're detectable across enormous cosmic distances. And they're not rare. Large surveys have found dozens of them, and they make up several % of the galaxy population at early cosmic epochs. Nobody predicted this. Not a single theoretical model published before Webb launched anticipated that so many compact red objects powered by overmassive black holes would populate the early universe in these numbers. How did these black holes get so massive so quickly? There are essentially two competing families of explanation, and Webb observations are beginning to distinguish between them. The first involves ordinary stellar physics applied at maximum efficiency. When very massive stars exhaust their nuclear fuel and die, they can collapse directly into black holes. These stellar mass black holes, containing perhaps 10 to 100 times the mass of the Sun, then grow by consuming surrounding gas and merging with other black holes. This is the standard picture of how supermassive black holes form, and it works well for explaining the black holes we see in galaxies at moderate redshifts. The problem is time. Growing a black hole from a stellar mass seed to millions or billions of solar masses requires sustained accretion over long periods. Even at the theoretical maximum accretion rate, called the Eddington limit, defined as the rate at which radiation pressure from the infalling material becomes strong enough to push back against further accretion. The growth is exponential, but still takes hundreds of millions of years under ideal conditions. For the little red dots and their overmassive black holes to exist when the universe was only 500 to 700 million years old, growth from stellar seeds would have had to proceed at essentially maximum efficiency continuously from nearly the moment of the Big Bang, with no interruptions, no periods of reduced accretion, no mergers that might temporarily disrupt the gas supply. That's not impossible, but it requires very special conditions that seem unlikely to apply consistently to the large population of overmassive black holes Webb is finding. The second family of explanations proposes that some black holes didn't form from stellar remnants at all. Instead, massive clouds of gas in the early universe could have bypassed the star formation stage entirely, collapsing directly into black holes without first forming a star. These so-called direct collapse black holes would start out with masses of perhaps thousands or even millions of solar masses, and could grow quickly from there. The conditions required for direct collapse are specific. The gas cloud needs to be exposed to enough radiation to prevent molecular hydrogen from forming, because molecular hydrogen is an efficient coolant that normally triggers fragmentation of the cloud into smaller pieces that form stars rather than a single massive black hole. If direct collapse black holes exist, they would be born large, and would explain why some of the early universe black holes appear to have had no time to grow from stellar seeds. Several spectral features observed in some little red dot host galaxies, including low levels of chemical enrichment in the surrounding gas, suggest that these systems didn't go through many generations of star formation before the black hole became dominant. They look pristine, as if the black hole formed from essentially unprocessed primordial gas. The positioning of little red dots within the cosmic web adds another dimension to the mystery. The cosmic web is the large-scale structure of the universe, the vast network of dark matter, filaments, and sheets along which galaxies cluster, separated by enormous empty voids that can span hundreds of millions of light years. When astronomers mapped the spatial distribution of little red dots relative to the surrounding galaxy population, they found that these objects cluster together in specific locations within the web, occupying particular nodes and filament regions rather than being randomly scattered. More evolved galaxies tend to appear at the densest nodes where multiple filaments intersect. Little red dots occupy moderately dense regions along filaments. This environmental dependence provides clues about what conditions favor their formation and suggests that whatever process creates them is connected to the local density and gas content of their environment rather than being purely a matter of chance. The overmassive black holes interact with their host galaxies through a process called feedback that has consequences extending far beyond the black hole itself. As the black hole consumes gas, it releases enormous amounts of energy in the form of radiation and powerful outflowing winds that propagate through the host galaxy and sometimes beyond it into the surrounding intergalactic medium. In some of the little red dots Webb has observed, the spectra show emission lines with distinctive broad wings indicating gas moving at thousands of kilometers per second, fast enough to escape the gravitational pull of the host galaxy entirely. This feedback may explain why the galaxies hosting overmassive black holes remain so small and faint compared to what their black hole mass would suggest they should contain. The black hole turns on early, consuming gas rapidly while simultaneously blasting away the gas that would otherwise have formed stars. The host galaxy is stunted by its own central engine. The black hole essentially monopolizes the available gas supply for itself while preventing the surrounding galaxy from growing. Only later, after the black hole exhausts the nearby gas and quiets down, can star formation proceed at normal rates and gradually build up the galaxy's stellar mass toward the proportions we see in modern galaxies. While the overmassive black holes were creating confusion in the early universe, Webb was simultaneously making discoveries about the space between stars in our own galactic neighborhood that completely transformed our understanding of interstellar structure. In 2025, the telescope was pointed at a supernova light echo near the Cassiopeia, a supernova remnant, the scattered remains of a star that exploded in the 1600s and left behind a beautiful but violent, expanding shell of hot gas visible at radio and X-ray wavelengths. The light from that ancient explosion had been traveling outward in all directions for 350 years. In 2025, part of that expanding pulse of radiation reached a cloud of interstellar dust and gas that had nothing to do with the original explosion. This unrelated cloud happened to be positioned in the right place, and the supernova's ancient light pulse illuminated it from within as it passed through. Webb captured the result in extraordinary detail. What the telescope showed was not the diffuse, featureless cloud that astronomers expected to find in the space between stars. Instead, the illuminated interstellar material revealed itself as a set of tightly packed sheets, organized layers of material stacked with the regular structure of wood grain or geological strata. These sheets showed structure on scales of about 400 astronomical units, which is less than 1/100th of a light year. For comparison, our entire solar system out to the orbit of Neptune spans about 120 astronomical units. These were features only a few times larger than our planetary system in the physical dimensions of their individual sheet structures, far smaller than anything astronomers had previously been able to resolve or even suspected existed in interstellar clouds. One scientist who worked on the analysis described the appearance as an onion with nested shells, layers upon layers of organized material, revealing that the space between stars has a degree of internal complexity that was completely hidden from previous observational capabilities. The light echo technique that made this observation possible works in essentially the same way that an audio echo works, except with light and on vastly larger scales. When you shout in a canyon, your sound bounces off the walls and returns to your ears as a delayed copy of your voice. A light echo reflects off interstellar material and reaches your telescope as a delayed and redirected copy of the original flash. As the expanding pulse of light from the old supernova moves outward at the speed of light, it progressively illuminates more distant material along its expanding shell, creating a visible echo that moves through the interstellar environment over years and decades as seen by telescopes on Earth. The technique acts as a cosmic searchlight, briefly revealing structures that would otherwise remain completely invisible in the darkness between stars, illuminated only by the diffuse background starlight that doesn't provide enough directional contrast to reveal internal structure. The sheets Webb observed in the Cassiopeia echo are likely shaped by two main physical processes operating simultaneously. Magnetic fields thread through the interstellar medium throughout the galaxy, and charged particles and dust grains tend to align along these field lines because of the electromagnetic forces acting on them. As the gas moves and turbulence stirs the medium, these magnetically aligned structures persist and accumulate, creating elongated formations oriented with the local field direction. Over long periods, this magnetically guided organization produces the layered appearance Webb detected. Turbulence in the interstellar gas also contributes to the structure. Gas in the interstellar medium is constantly stirred by supernova explosions, stellar winds, the gravitational effects of passing massive objects, and instabilities in the rotating disk of the galaxy. Turbulence naturally generates structure across a wide range of scales simultaneously, from the largest scales of entire cloud complexes down to the smallest eddies where the turbulent energy is finally dissipated as heat. The interplay between magnetic structuring and turbulent mixing creates the complex layered appearance that Webb revealed. The practical implications of this discovery extend beyond aesthetics. Stars form when dense interstellar gas clouds collapse under gravity, and the details of how that collapse proceeds depend on the internal structure of the cloud. If the gas is organized into sheets rather than smooth uniform density distributions, the collapse process can proceed differently than models assuming smooth initial conditions predict. Sheets can fragment into filaments along their edges and intersections. Filaments can break up into dense cores, and each dense core can become a forming star or a binary or multiple star system. The hierarchical structure Webb revealed in the Cassiopeia light echo may be a fundamental template for the internal architecture of star-forming regions throughout the galaxy and possibly throughout the universe. Understanding how matter organizes itself in interstellar space is fundamental to predicting where new stars form, how many form simultaneously, and what distribution of masses they have. On March 14, 2025, a gamma-ray detector in space recorded a flash of high-energy radiation lasting several seconds. The burst triggered automatic alerts that went out to observatories around the world, and within hours ground-based telescopes were tracking the fading afterglow. The measurements quickly revealed something extraordinary. This explosion had occurred when the universe was only 730 million years old. The light had been traveling through expanding space for more than 13 billion years before reaching our detectors. It was one of the most distant gamma-ray bursts ever detected, and Webb turned its attention to the fading afterglow 110 days after the initial detection, when the host galaxy itself became the main object of study. Gamma-ray bursts lasting several seconds originate from the deaths of massive stars. When a star more than about 20 times the mass of our Sun exhausts its nuclear fuel after a lifetime of a few million years, the core can no longer support itself against gravity. The iron core that forms at the end of the fusion chain cannot generate energy through further fusion because fusing iron requires rather than releases energy. The core collapses in less than a second, imploding to form either a neutron star or a black hole. The outer layers, suddenly deprived of the pressure support that had been holding them up, crash inward at speeds approaching a quarter of the speed of light. They hit the dense, collapsed core, bounce off in a titanic shockwave, and explode outward as a supernova. In the most massive stars undergoing the most extreme collapses, the implosion also generates powerful jets of material along the rotation axis that punch through the collapsing star at nearly the speed of light and produce the gamma rays. When one of these jets happens to point toward Earth, we detect a gamma ray burst. The jet is essentially a cosmic searchlight of the most energetic radiation in the universe, and we only see the burst when the beam happens to sweep across our location. What made this particular detection scientifically extraordinary was the distance. Observing a massive star die at a time when the universe was less than 6% of its current age provides a window into stellar physics under conditions radically different from those in the modern universe. Stars in the early universe formed from gas containing almost no heavy elements. They were composed essentially entirely of hydrogen and helium, the primordial products of Big Bang nucleosynthesis. Modern stars form from gas enriched by generations of previous stars and contain significant fractions of carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements. These heavy elements affect how stars structure themselves internally, how efficiently they radiate energy, how they evolve as they age, and how they die. Early universe stars lacking these elements should behave differently, and their deaths should potentially look different from the deaths of modern metal-enriched massive stars. The spectral analysis of the ancient afterglow showed the chemical fingerprints of silicon, oxygen, and iron in the expelled material, elements produced by nuclear fusion in the dying star and scattered into space by the explosion. This means that even the very earliest massive stars were capable of building heavy elements through fusion and distributing them into the surrounding interstellar medium through their deaths. The ancient supernova also looked remarkably similar to modern supernovae in its brightness evolution and spectral characteristics over the 110 days Webb monitored it. One team compared it directly to a well-studied nearby supernova and found close matches in brightness, spectral shape, and temporal evolution. This similarity is both reassuring and puzzling. Reassuring because it suggests that the fundamental physics of massive stellar death has not changed over 13 billion years of cosmic history. The same basic process, core collapse, bounce, jet formation, works the same way in the early universe as it does today. Puzzling because early universe stars formed in such different conditions that different outcomes might have been expected. The host galaxy of this ancient explosion is itself informative about conditions in the early universe. It's small and faint, barely detectable even with Webb's capabilities, appearing as a dim smudge around the fading supernova afterglow. This tells us that massive stars, the kind that die as gamma-ray bursts, were forming and dying in some of the smallest and least developed proto-galaxies in the early universe. These tiny systems, containing perhaps a few tens of millions of solar masses in stars, may have been the primary drivers of the heavy element enrichment that made subsequent generations of stars and eventually rocky planets possible. Every supernova in every small early galaxy scattered iron, carbon, oxygen, silicon, and dozens of other elements into the surrounding gas, gradually building up the chemical complexity that we take for granted in the modern universe, and that was ultimately necessary for the formation of Earth and the chemistry of life. The earliest confirmed black hole merger ever detected came from a system called ZS7, a galaxy that existed 740 million years after the Big Bang. When astronomers examined Webb images of this system, they noticed that it appeared to have two distinct bright cores rather than the single central brightness concentration typical of most galaxies. Initial examination raised the question of whether this was a single galaxy with unusual star formation or dust distribution. Then they analyzed the spectrum in detail and found the definitive answer. Fast-moving gas near both bright points, gas moving at velocities of hundreds of kilometers per second in tight orbits, created spectral signatures that astronomers recognized as the signature of matter falling into a black hole. As gas accelerates toward an event horizon, the intense compression and friction heat it to millions of degrees, and this hot material produces characteristic emission at specific wavelengths that can be identified unambiguously in a spectrum. Both cores showed this signature independently. ZS7 contained two supermassive black holes orbiting each other at close separation, both actively consuming surrounding gas, both blazing with the energy of infalling material. The two black holes are spiraling inward under the influence of their mutual gravitational attraction, gradually losing orbital energy and moving closer to each other on a trajectory that will end in a merger. The energy loss that drives this in spiral happens through the emission of gravitational waves, ripples in the fabric of space-time that propagate outward from the orbiting pair at the speed of light. As the two massive objects circle each other, they warp space-time around them in a rotating, oscillating pattern that spreads outward as gravitational radiation. This process was predicted by Einstein's general theory of relativity over a century ago, confirmed experimentally by the LIGO detectors in 2015 through the detection of gravitational waves from merging stellar mass black holes, and is now understood to be a universal phenomenon occurring whenever two massive compact objects orbit each other in close enough proximity. Current gravitational wave detectors on Earth are sensitive to mergers involving stellar mass black holes and neutron stars in the relatively nearby universe, where the frequency of the gravitational waves falls in the range where kilometer-scale interferometers can detect them. Supermassive black hole mergers, like the one developing in ZS7, produce gravitational waves at much lower frequencies, roughly in the millihertz range, that require space-based detectors separated by millions of kilometers to observe. The planned LISA mission, a space-based gravitational wave observatory being developed by the European Space Agency, will be sensitive to exactly this kind of signal. Once operational, LISA will detect supermassive black hole mergers throughout most of the observable universe, measuring their rate and mass distribution and determining how much of the mass growth of the supermassive black holes in today's galaxy centers came from mergers versus ongoing gas accretion. The ZS7 system discovered by Webb represents exactly the kind of early universe merger that LISA will eventually be able to detect in large numbers. The co-evolutionary relationship between merging galaxies and their black holes plays out over timescales measured in hundreds of millions of years. When two galaxies collide, their stars rarely actually collide with each other because stars are tiny compared to the distances between them, even within a dense galaxy. The stars pass through each other, their orbits perturbed by the collective gravitational field of the combined system, gradually settling into a new configuration. The gas clouds in the colliding galaxies do collide, crashing together at high speeds, compressing and heating the gas, and triggering massive bursts of star formation as the compressed gas reaches the densities needed to collapse into new stars. Over hundreds of millions of years, the two galaxies merge into a single combined system, with their stellar populations now orbiting together in a larger galaxy. The central black holes of each original galaxy sink toward the center of the merged system through a process of dynamical friction, gradually transferring their orbital energy to surrounding stars and gas. Eventually, they reach close enough separation that gravitational wave emission becomes the dominant energy loss mechanism, and they spiral inward to a final merger. The redshift measurement for the Jades galaxy at 1432 is one of the most extreme measurements ever achieved in observational astronomy, and deserves a careful explanation of what it means physically. When astronomers measure the redshift of a galaxy, they are measuring how much the wavelengths of light from that galaxy have been stretched during the journey from the galaxy to Earth. The stretching happens because the universe has been expanding while the light was traveling. Every wavelength gets multiplied by the same factor, which is 1 plus the redshift, a redshift of 14. 32 means every wavelength has been multiplied by 15.32. Light that left Jades as ultraviolet radiation at 121.6 nanometers, the wavelength of the Lyman alpha emission line from hydrogen, arrives at Webb as infrared radiation at about 1,860 nanometers. The universe is 15.32 times larger today than it was when Jades' light began its journey. Every cubic meter of space has expanded to 15.32 cubed meters, meaning the total volume of the universe has increased by a factor of about 3,600 since Jades' light was emitted. Measuring such extreme redshifts requires obtaining a spectrum of the galaxy, splitting its incoming light into component wavelengths and identifying the positions of known spectral features. This is technically demanding at these distances for several reasons. The galaxy is extraordinarily faint, its light diluted by both the vast distance and the expansion of space that reduces the energy of each photon and slows the rate at which photons arrive. Obtaining a useful spectrum requires collecting enough photons to measure their wavelength distribution with sufficient statistical quality to identify features reliably, which at these distances requires hours or even tens of hours of exposure time. The deepest fields Webb has observed, including the Jades fields that produced the Jades galaxy discovery, represent investments of more than 70 hours of telescope time, an enormous commitment for a facility where observing time is precious and oversubscribed. The observable universe sits at approximately 46 billion light-years in radius, a number that confuses many people who hear it for the first time because the universe is only 8 billion years old. If light has been travelling since the Big Bang, how can we see things 46 billion light-years away? The answer requires understanding how cosmic expansion affects the relationship between distance and look-back time. When the most ancient light we can detect was emitted, the object that emitted it was much closer to us than it is today. The universe was much smaller then. During the 13.8 billion years that light has been travelling toward us, the universe has been expanding, and the object that emitted the light has been carried farther away by that expansion. The 46 billion light-year figure represents the current distance to the most ancient objects, accounting for all the expansion that has occurred since their light was emitted. The light travel time of 13.8 billion years represents how long the journey took. The current distance represents how far away the source now sits after all the expansion that occurred during those 13.8 billion years of travel. The Hubble constant measures the current rate of expansion of the universe in units of kilometers per second per megaparsec, where 1 megaparsec equals about 3.26 million light years. This single number is one of the most important parameters in cosmology because it sets the scale of the observable universe, determines the age of the universe from the expansion history, and constrains models of dark energy and the ultimate fate of the cosmos. Measuring it precisely has been a central goal of observational cosmology for nearly a century, since Hubble himself first established that the universe was expanding and made a rough determination of the expansion rate in 1929. Modern measurements use two fundamentally different approaches, and in one of the deepest puzzles currently facing cosmology, they disagree. The first approach analyzes the cosmic microwave background, the relic radiation from 380, zoos and years after the Big Bang, that fills the entire sky with a nearly uniform glow at microwave wavelengths. The pattern of tiny temperature fluctuations in this ancient light encodes detailed information about the composition and geometry of the early universe, which can be used together with the known physics of how the universe evolves to predict what the expansion rate should be today. This method consistently yields a Hubble constant of about 67, 4 kilometers per second per megaparsec. The second approach measures the distances and recession velocities of galaxies in the relatively nearby universe using standard candles. Objects whose intrinsic brightness is known independently so that apparent brightness can be converted to distance. Cepheid variable stars pulsate with periods that are tightly correlated with their intrinsic luminosity, making them reliable distance indicators for galaxies within a few hundred million light-years. Type Ia supernovae used at greater distances have consistent peak brightnesses that make them useful distance indicators across most of the observable universe. This local measurement approach consistently yields a Hubble constant of about 73 kilometers per second per megaparsec. The discrepancy between 67.4 and 73 amounts to about 9%, which sounds small but is enormous when both methods have achieved internal precision better than 2%. The measurements are not overlapping within their uncertainties. They're pointing at genuinely different values, and the discrepancy has not gone away as both methods have been refined with more data and better instrumentation. This disagreement is called the Hubble tension, and it is currently one of the most actively studied and intensely debated problems in all of cosmology. Either our model of the early universe contains an important error that affects the prediction from the cosmic microwave background, or our local measurements contain a systematic error that inflates the locally measured value, or there is physics operating somewhere in cosmic history that our current models don't include, and that changes the expansion history in a way that reconciles the two measurements. Webb was hoped by many astronomers to resolve the tension by providing more precise local measurements than were possible with the Hubble Space Telescope. It studied more Cepheid variable stars in more galaxies with better infrared sensitivity and sharper resolution than its predecessor. The result was unambiguous confirmation of the higher local value. Webb gets the same result as Hubble Space Telescope, about 73 kilometers per second per megaparsec for the local expansion rate. The tension is real. The most powerful telescope ever built has confirmed rather than resolved it. A recent study used 3 independent distance measurement methods simultaneously: Cepheid variables, the tip of the red giant branch method, and carbon stars, applying all 3 to the same sample of 10 galaxies. All 3 methods agreed with each other, yielding a combined Hubble constant of about 70 kilometers per second per megaparsec, a value slightly below the supernova-based measurement, but still significantly above the cosmic microwave background prediction. The agreement between 3 completely different techniques rules out the possibility that any single method has a large systematic error unique to that method. Something more fundamental is going on. The first stars in the universe were radically different from any star we have ever directly observed, and we have never directly observed them at all. Every star astronomers have ever studied in detail, whether nearby or in distant galaxies, contains at least some fraction of heavy elements produced by previous generations of stars. But before any stars had ever formed, there were no heavy elements except for the tiny trace amounts of lithium produced in the Big Bang itself. The gas that formed the very first stars was essentially pure hydrogen and helium, completely pristine, untouched by any previous stellar processing. Astronomers call these hypothetical objects population 3 stars, placing them at the beginning of the stellar classification system that runs from the most ancient metal-poor stars through progressively younger and more chemically enriched generations. Forming stars from pure hydrogen and helium gas is physically different from forming them in modern molecular clouds. Heavy elements like carbon and oxygen are efficient radiators of energy. When a dense gas cloud is compressed by gravity and heats up, carbon and oxygen atoms radiate away the excess energy efficiently, allowing the cloud to cool, contract further, and eventually fragment into many small, dense cores from which individual stars form. This cooling and fragmentation is what produces the distribution of stellar masses we see in modern star-forming regions, where the majority of stars formed have masses below that of the Sun. Without heavy elements to facilitate rapid cooling, the gas in the first star-forming clouds stayed hotter. Hotter gas is harder to compress into small volumes. The minimum mass needed to collapse and form a star was therefore much higher than it is today. Computer simulations of population 3 star formation consistently predict that these stars were massive, typically 50 to 500 times the mass of our Sun, with some models suggesting that the very first stars may have been even more extreme, reaching thousands of solar masses. Stars this massive live extraordinarily brief lives. A star 100 times the mass of the Sun exhausts its nuclear fuel in only a few million years, compared to the 10 billion year lifetime of a Sun-like star. These massive objects compressed hydrogen to temperatures where it fused to helium, then helium to carbon, then carbon through a chain of increasingly heavy elements until they built up iron cores that couldn't generate energy through fusion. At that point, the core collapsed in less than a second, and the resulting explosion scattered the star's enriched interior into the surrounding gas. The next generation of stars that formed from this enriched gas was slightly different, containing the carbon, oxygen, and iron produced by the population 3 supernovae. Each successive generation added more heavy elements to the cosmic inventory, and the chemical evolution of the universe began. Population 3 stars should have disappeared billions of years ago. They lived too briefly to survive to the present day, and even if some had managed to survive by having lower masses than predicted, they would have accumulated heavy elements from their surroundings over billions of years and would no longer be recognizable as primordial stars. But we can potentially see them directly if we look at galaxies from the first few 100 million years of cosmic history, before multiple generations of stars had enriched the interstellar medium beyond the primordial composition. Webb can observe such galaxies, and within them, the collective light of population 3 star clusters might be detectable through their distinctive spectral signatures. A galaxy called GNZ11, which existed 430 million years after the Big Bang, has shown spectral features in its outer regions that match theoretical predictions for star-forming regions dominated by population 3 stars. The evidence is suggestive rather than conclusive, requiring additional observations to confirm, but it represents the most promising current candidate for the first detection of the original stellar population that first brought starlight to the universe. Population 3 stars also played a critical role in ending the cosmic dark ages through the process of reionization. After the Big Bang, the universe was hot and ionized. As it expanded and cooled, electrons combined with protons to form neutral hydrogen atoms, and the universe became transparent but dark, filled with neutral gas that absorbed ultraviolet light efficiently. This period, from about 380,000 years to the first billion years after the Big Bang, is called the Cosmic Dark Ages. The first massive stars that formed produced intense ultraviolet radiation that ionized the hydrogen around them, creating bubbles of ionized, transparent gas. As more stars formed in more galaxies across the universe, these bubbles grew and merged, and the entire universe gradually transitioned from neutral to ionized. This epoch of reionization represents one of the most important phase transitions in cosmic history, fundamentally changing the transparency of the universe and allowing light to travel freely through intergalactic space for the first time since recombination. Webb is designed to study the reionization epoch directly by observing galaxies from redshifts 6 through 10, corresponding to the universe between 600 million and 1 billion years old, when reionization was in progress and approaching completion. The key measurement is the escape fraction of ionizing photons from early galaxies, the fraction of the ultraviolet radiation produced by young massive stars that actually escapes the galaxy into intergalactic space and contributes to ionizing the surrounding hydrogen. This fraction depends on the distribution of gas and dust within the galaxy, which can absorb ionizing photons before they escape. Webb spectra can constrain escape fractions through detailed analysis of emission line ratios and the overall spectral shape, and current results from multiple surveys suggest that many early galaxies had substantial escape fractions. Combined with the unexpectedly large number of bright galaxies Webb has found at high redshifts, this suggests that ordinary star-forming galaxies may have been the primary drivers of reionization, producing enough ionizing photons to complete the transition within 1 billion years of the Big Bang without requiring exotic sources like quasars or very massive population 3 stars to dominate the process. Gravitational lensing is perhaps the most powerful tool Webb has for studying the most distant and faintest objects in the universe. When a massive galaxy cluster sits between Webb and a more distant galaxy, the cluster's immense gravitational field bends the paths of light rays from the background galaxy. Light that would otherwise travel past Webb at an angle is deflected toward it, effectively increasing the apparent brightness and angular size of the background source. The background galaxy appears magnified, sometimes by factors of 10, 50, or even 100, depending on the alignment between the source, the lens, and Webb. This natural cosmic magnification allows Webb to study objects that would be completely undetectable without the boost, extending its effective reach to objects far too faint to observe directly. Webb systematically exploits this by targeting known massive clusters and studying the distorted images of background galaxies that appear as elongated arcs and multiple images surrounding the cluster. One cluster, called Hubble S1063, produced hundreds of lensed background galaxies in a single observation, with some of the most highly magnified examples dating to when the universe was less than 1 billion years old. Without the gravitational lensing, these galaxies would be invisible even to Webb. With it, they become accessible for detailed spectroscopic analysis, allowing measurements of chemical composition, star formation rate, ionization state, and other physical properties that paint a detailed picture of galaxy conditions in the early universe. The combination of gravitational lensing and Webb's capabilities led to one of the most visually striking and scientifically rich discoveries of the mission so far. A galaxy nicknamed the Firefly Sparkle because of its appearance in lensed images as a chain of bright points resembling sparks, was discovered in observations of a foreground cluster. Gravitational lensing magnified this galaxy by a factor of about 30, stretching it into an elongated arc and amplifying its light enough for detailed analysis of its internal structure. The galaxy existed about 600 million years after the Big Bang, and rather than appearing as a single featureless blob, as most galaxies from this era do, it showed 10 distinct star clusters arranged along its extended structure, each individually resolved by Webb's sharp optics combined with the gravitational magnification. Each of the 10 clusters in Firefly Sparkle has different properties. They have different ages, ranging from very young clusters, just a few million years old, to slightly older clusters that formed tens of millions of years earlier. They have different stellar masses, ranging from a few thousand to several 100,000 solar masses. The age differences between clusters tell us that star formation in this protogalaxy wasn't a single catastrophic event, but a series of distinct bursts separated by millions of years of relative quiet. This episodic pattern is consistent with theoretical models in which gas accumulates in a forming galaxy along cosmic web filaments in an irregular, bursty manner rather than at a constant rate. When enough gas accumulates to reach the critical density for gravitational collapse, a burst of star formation occurs. The massive stars formed in that burst blow away or heat the remaining gas through their radiation and eventual supernova explosions, quenching further star formation. Then the cycle repeats when more gas accumulates. The 10 clusters in Firefly Sparkle are a direct observational record of this cycle playing out over tens of millions of years in one of the universe's first proto-galaxies. The total stellar mass of Firefly Sparkle is only about 10 million solar masses, less than 1/10,000th of the Milky Way's current stellar mass. Yet the timing and mass are both consistent with what theoretical models predict for the Milky Way at a similar age. We may be looking at a direct analogue of our own galaxy in its very earliest infancy, a protogalactic fragment that would continue accumulating mass through star formation and mergers with other small protogalaxies over the following billions of years, eventually growing through hierarchical assembly into a massive spiral galaxy. Without gravitational lensing, Firefly Sparkle would have been a completely unresolvable point of light, far below Webb's detection threshold. With it, we can read its internal structure like a book, tracing the history of star formation in the building blocks of today's massive galaxies. In much closer cosmic territory, Webb conducted an observation that stands apart from the distant universe program, but that could potentially have profound long-term implications for humanity's understanding of our place in the cosmos. Using its mid-infrared instrument with a specially designed observing strategy to manage the overwhelming glare of a nearby bright star, the telescope examined the vicinity of Alpha Centauri A, the slightly larger of the two sun-like stars in the Alpha Centauri system, the nearest star system to Earth at just over 4 light-years distance. Alpha Centauri has fascinated astronomers and the public for decades as the first potential destination for any future interstellar mission. Proxima Centauri, the red dwarf third member of the system, already has 2 confirmed planets. But Alpha Centauri A and B have been much harder to study because they're intrinsically so bright that their light overwhelms any signal from potential planets. Webb detected a faint infrared source at roughly twice Earth's orbital distance from Alpha Centauri A. The signal is consistent with a large planet, possibly a gas giant in the outer region of the Alpha Centauri A system. The detection is currently tentative, requiring additional observations to confirm and to rule out alternative explanations such as background stars, instrumental artifacts, or scattered light from the star itself. But if confirmed, this would be the nearest exoplanet outside our solar system, beyond the small planets around Proxima Centauri, and it would be located in the system that humanity has long dreamed of visiting first in any far future interstellar mission. A gas giant at twice Earth's orbital distance might host moons, and large moons orbiting in the vicinity of a habitable zone can potentially develop liquid water on their surfaces. The discovery, if confirmed, would transform the Alpha Centauri system from an intriguing but uncertain target for planetary science into a system with a confirmed planetary architecture, offering potential opportunities for astrobiology as well as planetary science. In planet-forming disks around young stars, Webb has been conducting a systematic survey of the chemical inventory available for planet formation. One of the most significant results has been the detection of crystalline water ice in the outer cold regions of young planetary disks, specifically in the zone beyond what planetary scientists call the snow line, the distance from the central star at which water freezes and can exist as solid ice rather than vapor. The presence of crystalline ice with water molecules arranged in a regular lattice structure rather than the amorphous random arrangement of rapidly frozen ice indicates that the material in the outer disk has experienced enough thermal processing to allow molecules to reorganize into ordered structures. This requires either slow freezing or periodic warming events, perhaps from heating by the young star's variable radiation output, or from shock waves generated by the collapse of the disk itself during its early formation. The ice reservoir in the outer disk represents the raw material from which comets and icy planetesimals form, and from which water could eventually be delivered to inner rocky planets during the dynamic, chaotic era of planetary system formation. This delivery process is thought to have been critical for Earth. The inner solar system where Earth formed was too warm during planet formation for water to condense as ice, meaning Earth would have formed as a relatively dry, rocky planet. The water that now covers 71% of Earth's surface had to come from somewhere else, almost certainly from comets and asteroids that formed in the cold outer solar system and were then scattered into the inner solar system by gravitational perturbations from the giant planets. Finding abundant crystalline water ice in the cold outer regions of young planetary disks provides direct observational confirmation that the raw material for this water delivery process is indeed present in planet-forming systems around other stars, suggesting that water delivery to habitable zone rocky planets may be a common rather than exceptional feature of planetary system formation. Dark energy remains the deepest mystery that modern cosmology confronts. The discovery that the universe's expansion is accelerating was made in 1998 through careful study of Type Ia supernovae at various distances. By measuring both the apparent brightness and the redshift of these stellar explosions, two independent teams determined that the expansion of space has been speeding up rather than slowing down. This was completely unexpected. The gravitational attraction of all the matter in the universe should have been decelerating the expansion over time. Instead, something was pushing space apart with increasing effectiveness, overcoming gravity on the largest scales. This something was named dark energy, and subsequent observations have confirmed its existence and measured its properties with increasing precision. The simplest mathematical representation of dark energy is Einstein's cosmological constant, a term in the field equations of general relativity representing an inherent energy density of empty space itself. If space has an energy density, then as the universe expands and creates more space, more dark energy appears, and the total repulsive effect grows proportionally to the volume. The problem is that no one can explain why empty space should have the specific energy density we observe. Quantum field theory predicts that vacuum fluctuations should give empty space an enormous energy density, but the predicted value exceeds the observed cosmological constant by approximately 120 orders of magnitude. This is not a discrepancy that might be resolved by better measurements. It is the largest disagreement between a theoretical prediction and experimental observation in the history of physics, pointing to something fundamentally incomplete about either quantum field theory, general relativity, or both. Webb contributes to dark energy research by extending the supernova distance redshift relationship to greater distances and earlier cosmic times, tracking how the expansion rate has changed over billions of years. If dark energy is truly constant, the rate of change of the expansion rate should follow a specific pattern. If dark energy is evolving, the pattern should be detectably different. Current results from Webb, combined with those from ground-based supernova surveys and the dark energy spectroscopic instrument mapping the large-scale distribution of galaxies, are beginning to hint that dark energy may not be perfectly constant. The hints are not yet definitive, but they're present in multiple independent datasets, and If confirmed by future observations, they would require completely new physics to explain. Physics that goes beyond the cosmological constant and involves a dynamical field with its own evolution equation and potentially its own coupling to other components of the universe. The universe we're discovering with Webb is stranger, more complex, and harder to explain than the universe our best pre-Webb theories predicted. Galaxies in the early universe are too bright and too massive for their age. Black holes in early galaxies are too large for their host galaxies. The expansion rate can't be consistently measured by two rigorous independent methods that should agree. Little red dots appear in numbers that no model anticipated. The interstellar medium between stars has detailed internal structure that was completely hidden from previous observations. The first gamma-ray bursts from the cosmic frontier look remarkably similar to their modern counterparts, despite the profoundly different environments in which they occurred. None of these anomalies individually overturns cosmology, but together they paint a clear picture of a field being actively and productively challenged by new data. A field whose models were built from the observations available at the time, and that must now be revised to accommodate what the most powerful telescope ever constructed is revealing. This is precisely how science makes progress. You build the best theory you can with available evidence. You build better instruments. You make better observations. You find that the new data disagrees with the theory in specific ways. You revise the theory, make new predictions, and test them. Webb is providing new data at a rate and quality that no previous instrument could match. The theoretical revisions that will result from this flood of discoveries are already beginning, and the models being constructed to explain what Webb is finding will make new predictions that will be tested against the next generation of observations, both with Webb itself as it continues operating, and with future facilities that will build on what Webb has established. We are in the early years of the Webb era of astronomy, looking back at the first few years of a mission expected to last at least a decade. The discoveries already made are transformative. The discoveries that will come are impossible to predict in detail, but certain to be significant. Every few months, the distance record for the most ancient galaxy observed is broken. Every survey turns up objects that don't fit neatly into existing categories. Every deep field image contains surprises that spawn new research programs. The cosmos is not finished revealing its secrets, not to Webb, and not to the generations of astronomers who will spend careers analyzing the data Webb collects and building on the foundations it lays. Out there, at the edge of what light has had time to cross since the Big Bang, galaxies formed from nearly primordial gas in the first few 100 million years of cosmic time are still waiting to be found. Their ancient light, stretched almost beyond detection by 13 billion years of cosmic expansion, is still traveling toward us. Webb is collecting it, one photon at a time, building up images and spectra from the edge of time itself. What it finds there is rewriting the story of everything, and we are just getting started.